So far, we've taken you through light, through its Lambert beer, primary production. Then we added nutrients, then nutrients with a nice seasonal signal. And now we are going to add grazers to our simulation. So I'm just starting with our old code here that we made last time, and I'm just going to save as, and I'm going to make it Grazer code. And we're going to modify a couple things here. So let's go ahead and require fields. We're going to do that. And here's where we read our sunlight data in. Again, we can copy it down to here where we're plotting our 10 years of sunlight data. There it is, oscillating up and down. This is where we generate our mixed layer depth. Here, I think we'll set our standard deviation here to 0 first. For our mixed layer depth index. There's our mixed layer depth index and a nice seasonal signal. And here's where we create our depth vector. And the code below is where we did an example of what the nutrient field was going to look like, which was replicated later in the simulation. So we're just going to delete this here. We don't really need this from previous. That just takes some time up. So here's where we're gathering our fields that we need to collect the results of our model. We've got our underwater light field, primary production field, nitrogen field, growth rate due to nitrogen, growth rate due to carbon, our cell field, our total cell vector, how many there are in the water column, our attenuation, our diffuse attenuation coefficient fields, and the sum of our production, and also this is where we start our cell vector, our initial concentration of cells in the simulation. We need to add a couple things here before we go into cell vector, a few more fields. One is going to be the Graze response dot field. So this is going to be the functional response of grazers to the number of cells. So this object will hold individual grazing responses to the cell field. This is the functional response. All right, and that's going to be the result of a Michaelis-Menten function. Then we're going to see the Graz dot field. No. And this object will hold the number of cells grazed by the grazers. So how many were killed? How many of those phytoplankton cells were killed? The next is going to be capital G field. This object will hold the number of grazers, just like the cell field held the number of phytoplankton. And then we need the Graz dot mu dot field. This object will hold the growth rate of grazers. So that's going to be the numerical response. What's going to be the numerical response? We talked about that in lecture. And then we have the sum dot g dot vec null, and this object will hold the water column integrated grazer number. Okay, so we add those things. Let's save that real quick. And then here's where we start our initial cell vector. We're going to now do a zoo.vec. So this is our zooplankton. This is what our initial concentration of zooplankton will be. We're going to go ahead and repeat 1 and times is going to be 100. So we're just going to, basically I can just cut and copy this here. Instead of 10,000, we're going to repeat just 1. And this will be the initial Grazer vector. Okay. All right, so let's copy all this stuff, make sure there's no errors in it. Copy and run that. Yeah, all right, okay, so all those objects are now created. Let's scroll down here. Here we've got some constants. Here our primary production, EK, EB, our respiration, our nutrient and carbon, half saturation and mu max constants. Well, we need to do something similar for the Grazers. So we're going to do G max equals 1. And this is the max cells ingested per day at each depth bin. And these are numbers that I'm just kind of making up so the simulation runs, but you can change them however you'd like. So a GKM is going to equal 100,000. This is the cell concentration at for half of G max in the Michaelis-Menten equation. Remember, we could use Michaelis-Menten equation for nutrient uptake, and we're also going to use it here for the feeding rate. All right, and we can also use it for the growth rate of so these are for, I'll just put this, these below are for the functional Michaelis-Menten response. These below are for the numerical Michaelis-Menten growth response. I guess it's still a gradient response. So one has to do with how much they eat. One has to do with how much they grow based on how much they eat. I'm sorry, what their growth rate is based on how much they eat, and then we take that growth rate and we put it into an exponential equation. Okay, so we need to have G mu max 0.5. So this is the max growth rate of a Grazer. Right. And then we need to have G, capital GKM. See, these are now here for feeding. These are down here for the growth response. Got to keep these straight. Equals 1. So this is the Michaelis-Menten half saturation constant for growth rate, and GR equals 0.1. So this is going to be the fraction of Grazer biomass that go toward Grazer respiration and loss. So just like the phytoplankton have a loss term, the Grazers are going to have a loss term. All right, so these are all constants that we're going to fix here in our equation or in our simulation. And now we get down to the loop that is actually running the simulation, and we need to edit a couple things in here. What do we need to edit? Well, here's our NVec, our KVec. Is there anything else that we need to add in here before we get down to, right, so here's where we create our initial light vector, primary production, what our nutrients are, what our diffuse attenuation is like. This little internal one here is what we're solving Lambert-Beer and computing primary production. We are then reversing those because of the way we compute it. Then we've got our Michaelis-Menten function for nutrients, for carbon. And we do a little rinky-dinky stuff here to deal with the interaction of those two things. Then we grow our cells together. Then what we're going to do, once we grow our cells, we're going to break into here. And some of those cells now are going to die immediately from grazing. So now our Graz response is going to be a Michaelis-Menten function, G max times our cell. Remember, this is our maximum grazing rate. Our cell.vec, whatever that is, divided by G Km, so that's our half saturation constant for grazing, plus the cells dot vec. Right? So this is how many cells an individual grazer ate. All right, so then what we have is the grazing vector that's going to equal the grazing response, right, times how many zooplankton there are, how many grazers there are. Okay, so here we're just multiplying the number of grazers by the functional grazing response. Okay. Now, based on how much they ate, we need now to calculate the growth rate of the grazers. So that's going to be our G mu max, right, times how much they actually ate, which is our Graz dot vector, Graz vec. Let's go ahead and this here, divided by, remember this is the Michaelis-Menten form, our half saturation constant for grazing, Graz dot, whoops, I'm sorry. This should be Graz response. Okay, now we're going to take all of this. So this is our growth rate. Estimated growth rate is going to be our mu max based on times how much was actually ingested, half saturation plus how much was actually ingested. And here's where we're going to add our loss term minus our GR times G mu max. So that's just a loss term. So it's going to be some respiration based on what the mu max is in this case. Okay, now we need to rethink about our cell vector here. So here's what we got to do. Cell vector is, remember we grew some, cell.vec minus the grazing dot vector. All right, so that's just how much we grew. This is how much we ate. So our new cell vector has to respond to that, reflect that, and then to make sure that our code works, I'm going to put another line in here. So this is now our new cell vector after taking out cells that were eaten. New one here, new cell vector. We just have to do a little number handling, a little bookkeeping here. We're just going to replace cell.vec where cell.vec is less than 0 with 1. So what we're doing here is we're saying that we're going to replace any negative numbers with 1. It's just a coding trick to avoid negative cell counts. Always be some cell around. So here we go. I'm just going to copy and paste this comment in here. Replacing any negative numbers with 1. It's just a coding trick to avoid negative cell counts and to make sure there's always some cells around. All right. There are more elegant ways to do this, but this is just a homework model. Okay, now our zoo vector, right? Remember the zooplankton ate something, and we got a growth rate from them. We're just going to use a standard exponential. There are other forms that we're going to talk about in class, but I'm going to do zoo.vec, and you can mess around with those if you want, times exp. Graz.mu, which is our cell vector times 1. Okay, so this is now just computing the new Grazer vector based on limited Grazer growth rate. All right. Remember, we computed GrazU up here from this Michaelis-Menten function that was based on the Graz response. And the Graz response here was how many cells they ate, and that was based on the cell vector here. So there we go. And we adjusted the cell vector for how many were killed. All right, so now we just need to add a couple more fields down here. The Graz.response field is going to be rbind Graz.response field and the Graz response. This is going to be the Graz field. I'll put a note in here just so we can keep track. Collecting the response of individual grazers to the cell field. Right. Graz field is rbind field with Graz vector. Collecting the Grazer results, how many cells grazed, right? Okay, and the Graz.mu field rbind growth rates that we're calculating. Right? So this is simply and g dot field. Sum g is concatenating so similar to the way that this is spelled. Similar to the way that we're summing up the total primary producers or total phytoplankton, we're doing the same thing with the grazers. Right. Now, we'll see if I did this correctly. We'll go ahead and run this. See what happens. Oh, G mu max not found. I had it here as G mu underscore max. So I probably misspelled it in here. Here we go. Mu max. Okay, so let's try that again. Let's come back up to the very top. Another one. G mu max. Oh, there it is. So let's try this again. Graz.vec not found. Let's see if I missed something in here from my notes. I can do a search here. Yeah, I guess this should be Graz vector. Okay, yep. All right. Just come in here. Let's start from the top. All the way down now to the bottom of the loop. Okay, finding all kinds of little errors here. Here it is. It should be na.rm equals true. Okay, we'll try again. There we go. So our code has gotten more complicated. This is probably as complicated as our code will get during the semester. Okay, so now that that's done, we can come in here and let's go back to some of our old plots here. Let's image the light field. Okay, quite a bit different than what we've seen before. And before we can do is we can take a look at the light diffuse attenuation coefficient at the beginning, at the middle, and at the end of the simulation. Yeah, pretty interesting. Okay, so we can also come in here, image.plot sun time, z, and the cell field. Okay, so this looks pretty different. You can see that we've got all kinds of interesting patterns here in the cell field, and this is the point where we really have reached the limit of what we can do with the way that we have the model. We have no mixing in the model, so none of these cells are communicating with each other. They're not being mixed across. So what you can see here is that Grazer is starting to eat holes out of the population here at different rates. And so and that should be reflected if we just copy this in the G field. Yep, okay, so see the distribution of Grazers is rather odd. In fact, we can get a little better look at them if we put a log 10 in front of this. Yeah, see? Okay, so we're gonna have a little fun with this data. So we're gonna try something new here. We're gonna make a, let's clear our plots out here. Yeah, all right. So this code down here that we used for previous codes, we can take that out. All right. So let's plot now. Sun time and log 10 of the cell field, column 61. We do that, what does that look like? Okay, yeah, we see oscillations and cell concentration. Remember, this is in log 10 space. So we can see this. We can just put a ylab equals log 10 cells. You definitely see those oscillations there, and then kind of crashes and starts oscillating again. And 61, what's the number? The dimensions of cell field are this many time periods, rows, and the columns are 101, which corresponds to the length of z. So length 61, right here, here's the 61st element, is at 40 meters deep. 40 meters deep. So if we do z 61, we get the depth of minus 40. So that's what this is here, 40 meters. All right, let's try something else here. Let's do plot. Actually, we can just copy and paste this. Log 10. Let's do the G field. And let's make the color equal red. Go ahead and plot that. Okay. We see Grazers kind of have this oscillation and then come up, and they kind of go down and they come up. Remember, this is in log 10 space. So we have Grazers that are very small. Very, very, very low numbers. And we can plot do this now. Let's plot, take this out. Let's put this as the x-axis. All right, so now we're just plotting the Grazers versus, the cell field versus the Grazer field. And let's just do type L. Okay, we got some circles going on here. Interesting. So we have some kind of phase cycle going on here. Possibly Michaelis-Menten. We could probably take a look at a bunch of different depths at this area. And what's interesting here is that we can layout. Use a layout command. What this does, makes a matrix 1 through 3, 3 rows, 1 column. And then what this is going to do, this bit of code, two, 3, vertical stacked plot. So if you remember from very early on, when we looked at matrices, there's a matrix of 1, 2, 3. All this layout function is going to do is say there's going to be a plot in the upper third, the second, and the bottom third for your next 3 plots. So when we do this together, we can make, there's sun time, grazers, and then the circles here. In fact, we can mess with some of these X and Y's here a little bit. Let's see, what can we do? I'm going to set the plotting margins. 3, 3, 3, 3. Yeah, get a little more in there. Looks like we lost some of our labeling, so maybe we want to. So this is the bottom one, so let's do that 4. Bottom left margin 4. Top margin, let's make that 2. Right margin is 2. It's a little nicer, a little bit nicer. Okay. So for the rest of the things that we're going to do, I'm going to direct you over to the homework.